Okay. So we learned about deformation gradient. It's a matrix where individual components are the derivatives of the deformed coordinates partial derivatives rather to the coordinates from the undeformed configuration. Actually, these two x i's and xj's represent configurations. Okay, and then we defined something called green strain, which looks like this. And we discussed that a body undergoing rigid rotation and translation, rigid rotation and rigid translation, would have the small x for each and every point on the body. So imagine this is v0 and this is v. So the coordinates here are capital X, whereas the coordinates here for the same point being mapped at two different locations is small x, and we are actually trying to take derivatives of small x. Okay, and what does f represent? D small x is f d capital X. For instance, at P, if I take a tiny differential element of d capital X, that maps as d small x in the deformed configuration. And now this infinitesimal element could be taken in any direction. Um, and that's why we need a matrix to represent the derivative. So there are three independent components of d capital X, and there are three independent components of d small x. And how do they relate? Using this matrix. It's a 3 by 3 matrix, and small x for rigid translation and rotation could be represented using an orthogonal tensor multiplying the original configuration plus a time dependent simple translation. If q were not there, if q were something like an identity, then x would be capital X plus ct, which would basically mean the object is having a rigid translation everywhere. So the amount of displacement is same everywhere. And as you can imagine, if the amount of displacement everywhere is the same, there is no strain developed in the material. Now, in addition to rigid translation, this also, if you incorporate q, then you have the rigid rotation. Um, so as you can see, so q are so-called orth plus tensors, which is the set of all rotation tensors. And also I belongs to the same group. Basically I is one of the q's. So what is the definition of q? Q times q transpose equals q transpose q, and both equates to an identity matrix. So basically the transpose of this quantity is inverse of it, of this quantity. So then we showed that determinant of q with this definition should be either plus or minus 1. And then we say the ones that give you determinant equal plus 1 are actually the true rotation tensors. Then we also showed that QU dot QU is essentially U dot U or U squared, which basically tells us that once you pre-multiply u with this q matrix here, the magnitude of the vector doesn't change. Okay, so what it does, so any tensor multiplying to a vector does some linear operation. Okay, let's say t v time equals u is a set of linear operation being performed on different components of v to get u. For example, if you multiply a vector uh, with a simple scalar like 5 times u, that could also be thought of as being multiplied to this matrix right here, 555 0 0 0 0 0 0, basically 5 times I. So this is a matrix multiplying u. So any set of linear operation on a vector which gives you a second vector can be thought of a matrix multiplication. And So this is a general form, and as it turns out, Q is such a matrix that when you do this operation, set of linear operation, so it doesn't change the magnitude of the vector. All it does is then left is all it does is rotate. So it just rotates a given vector, not changes magnitude. uh, the other proof being that if you do qu dot qv, it can be shown that this is same as u dot v. All of this come from this very definition right here. It's a definition actually, and here I'm using the definition sign. So these are all but corollaries of that definition. So again, as you can see, if the dot product of two vector mm, is, as we know, is the magnitude of the two vectors, and basically the cos alpha between u and v. And as we have discussed earlier, that this by definition is also qu uh, times qv, because it's a dot product, times cos alpha between qu and qv. Now the thing is, we know that this quantity right here, qu magnitude, is essentially the magnitude of u. So if you cancel either side, then you left with that the angle all between the two vectors doesn't change as well. So once you perform, so imagine u is this vector, and then v is this vector. So when you perform q over u, maybe u is something like this, the same length but different orientation. Maybe v is something like this, but the angle between the two doesn't change. Okay, so that way we know that q is a rigid rotation, represents rigid rotation, or it essentially performs rotation of a vector. So when you have your small x represented like this, which is the general form for rigid translation and rigid rotation, so then you know your deformation gradient is essentially this quantity, q itself. Okay, and then if you substitute that to the expression for green strain for this particular case, which is rigid translation and rigid rotation, it turns out to be q transpose q minus identity. Uh, and then this q transpose q, by definition, is an identity matrix, and therefore what you are left with is a zero matrix. That means a 3 by 3 matrix with all components equal to zero. So basically, as you can see, that the green strain doesn't fetch any strain. Green strain is a measure of strain, and at this point I should also mention that we have already discussed also that a strain measure is up to the user. Okay, one can decide a strain measure, whereas the stress measure pops up on its own from the solid mechanics formulation that we have seen in one of our previous classes. So the strain measure is up to the user, but there are certain rules to using a strain measure. So this strain measure, there was not a very concrete way, but a vague way we define this strain measure. If you follow the class notes, but then this doesn't fetch any strain if a material is undergoing rigid translation and rigid rotation, which is kind of expected. And since it fulfills that expectation, therefore it is a true strain measure. Here I'm not talking about the logarithmic strain or true strain, which is like ln of 1 plus uh, engineering strain. Okay, all of these are uniaxial, by the way. Here I'm talking about a multi-axial strain formulation or a strain representation that is true to the acknowledgement of deformation. If there is rigid translation and rigid rotation, there is no strain according to this measurement. Okay, that's where the true strain word comes from. So it's a true strain measure. Okay, don't confuse the logarithmic strain and the green strain here. Okay, that being said, what is not a true strain measure? Um, our so-called small strain measure. Okay, now now we looked into the undeformed and the deformed configuration. So this is the configuration at t equals 0, also known as v0, and there's a v configuration at t equals sometime t. Okay, and we said that uh, see, the reference frame and coordinate are the same for either cases. All you are doing is looking at the configuration, the undeformed configuration and the deformed configuration from the same coordinate system. So this is the coordinate from the undeformed configuration, and this is the coordinate from the deformed configuration for the same point. Now, the difference between the two can be thought of as the displacement. That is actually the displacement. So uh, small x could be thought of capital X plus u, and then deformation gradient f, which is or could also be represented as, this sign, right? This is nabla.
Yes, sir.
Grad of small x with respect to capital X, which means the individual terms are small xi, capital Xj. So I, of course, represent the row, and J, of course, represents a column. So you can fill up the ijth column. So this basically consists of gradient of capital X with respect to capital X, and then gradient of U with respect to capital X. Now, um, normally I would ask what should this quantity be, but this
This
is
is I.
revisiting. So I'll
This is
directly
I.
give you the answer. It's the identity matrix. So if it were a scalar whose derivative you are taking with respect to the same quantity, like dx, that would be 1, or del x, that should be 1. Okay, but it's a vector. Okay, and you are taking gradient of another vector, and when you take a gradient of a scalar with respect to a vector, then you have a vector. And when you take the gradient of a vector with respect to a vector, as we have seen earlier with deformation gradient, you get a matrix. And in this case, the matrix is mm, the equivalent of 1 in the metric space, which is the identity matrix.
Unity matrix.
Okay, and then you have the gradient of u. But imagine your u were, if u were small. Okay, and that implies even grad of u were small. See, if u were small, then small x is essentially uh, not very different from capital X. Now, I'm not acknowledging that no, it's not that I'm not acknowledging that there is a difference between small x and capital X, and that deformation is u. That is not how what I'm doing. All I'm trying to say here, this gradient, okay, whether you define with respect to the deformed configuration or the undeformed configuration, okay, they basically turn out to be the same quantity. Okay, and so in a way we can simply denote them with grad of u with respect to one set of coordinates. Okay, it doesn't matter whether deformed or undeformed. Imagining if you were really really small, how small is really really small, that we will discuss in a minute. So then we can say that this green strain. Now the expression I'm about to write is a general expression of green strain. Okay, using the idea that f is I plus grad of u, and even if u were not really small, then the green strain would still be this quantity I plus grad of u plus grad of u transpose plus grad of u transpose grad of u minus the identity matrix. And these two surely cancel out. So I'm left with, so this could be written again. Here I'm writing a general form where you may or may not be much smaller compared to the dimension of the geometry. So there is grad of u plus grad of u transpose plus order grad of u squared. Okay, so now at this point also I'm still writing the general form, but now if I say limit uh, u tends to 0, e, so this one is order grad of u squared, so e could be said to be approximately same as the small strain of ours, which is defined as half of grad of u plus grad of u transpose. Or in other words, epsilon ij is del x del u I del xj plus del uj del xi times half, which basically means epsilon xy, oh sorry, not xy, epsilon xx is del ux del x. So this will happen twice and then multiply with half. So it is del ux del x, and epsilon xy would be del ux del y plus del uy del x multiplied by half. Okay, this is what is known as the tensorial representation of strain. Okay, there is also an engineering representation of strain, and please don't confuse that with engineering strain. Okay, so that is altogether a different subject. Here we are, I mean, that is in relation to considering that the length is also updating with deformation taking place. Here we have multi-axial strain, and we are learning how we can represent that in a vector form or in a matrix form. So so the by the very nature of the way we have defined strain in whether it is green strain or small strain, they are all symmetric tensors, which basically means in a 6 by 6 matrix there is 1 plus 2 plus 3, total 6 independent components, not 9, because the strain tensor is symmetry, which basically means I can represent the strain as a vector which kind of looks like this. epsilon zz, gamma xy, gamma yz, gamma zx. So by symmetric, I mean that epsilon xy is also epsilon yx, and that you can check from this expression. Substitute x for y and y for x, and you will get the same expression, uh, and so on. So what we do here essentially, we just add the two off diagonal terms. So essentially, we have epsilon equals epsilon xx, epsilon yy, epsilon zz, epsilon xy, epsilon yx, epsilon xz, epsilon zx, epsilon yz, epsilon zy. Okay. So what do we do is we go and add this equal terms which are off diagonal. Okay, we simply add them up and make a single term because they are symmetric and all. So this quantity here is twice epsilon xy and so on. So this thing is also known as Voigt notation. Okay. Now, what is the deal with the small strain? Is it a true strain measure? If I substitute f equals q, that implies grad of u. See, if small x is q times, actually this q, by the way, is a function of time. Okay, q of t times capital X plus c of t. See, this coordinate from the undeformed configuration, that is not a function of time because that is at t equals 0 specified. Um, so these two terms, so the rotation could be changing with time. So if initially it is tilted by an angle of 30 degree, it could be 60 degree after a while. So the rotation is dependent on time. So if the body is having a rigid translation and rotation, then the deformation gradient is q, and gradient of u becomes q of t minus I. Okay, and then if I substitute that into the expression of small strain, see, it's not that the small strain measure only exists when u is small. The small strain measure is a measure you define, okay, and that exists always, just like green strain. It just turns out that when u is really small, that the green strain is essentially same as a small strain. And now you'd see when we are not having that condition, okay, does the small strain measure, okay, still measure up to its potential, or does it really true strain measure? That's what we want to check. So then this quantity becomes half of q minus I plus q transpose minus I. And no, this quantity is not equal 0. It is simply q plus q transpose minus twice I. And that's not trivially 0. Okay. So this is not a true strain measure. Okay. But hold on. Is it totally an incorrect strain measure? Is it totally meaningless? Now we talked about having small u. What we really meant was that if we see the displacement in part could be translation. Now translation, of course, is filtered out. Whenever you have the deformation gradient, okay, this c doesn't appear in the expression of f. So that is already taken care of. So the rigid translation doesn't make any change to whether you have small strain measure or green strain. It's a rigid rotation that is important. Now for the amount of deformation that the object is undergoing, the rotation must be small, in order in order for green strain to make, sorry, in order for small strain to make sense. And that's what we are going to prove. Imagine you are talking about the rotation about z axis by an angle of theta. Then q would look something like cos theta sine theta minus sine theta cos theta 0, 0, 1, 0, 0, 1. And you can check that if I multiply this with E1, okay, what is E1? E1 you can say is essentially 1, 0, 0. Okay, then I'll have a matrix. Then essentially I'll have the first column. You can check that. So cos theta minus sine theta 0. So okay, I think I need to do some correction. Possibly this is what would have the minus sign, and this one should not have the minus sign. So so you have cos theta sine theta 0. So earlier imagine u1 being aligned along the x direction. Now it has become, let's call it u1 star, rotated by an angle of theta. You take q times e2, that would be minus sine theta cos theta 0. So earlier it was this vector e2. Now by multiplication with q, you have now got this vector right here, e2 star. And the angle between e1 star and e2 star, you guessed it right, remains the same, 90 degrees. What happens if I multiply with e3? I get the third column, which is that e3 doesn't change, because e3 to start with was 0, 0, 1, and it doesn't change. It's because e3 is essentially the axis for this rotation tensor. Now imagine, so all I'm trying to show here is that there is a definitive way to find out what the Q matrix should be if it represents a rotation about a certain axis. Okay. Now, in the limit theta tends to 0, Q could be written as 1, 1 minus theta, theta 0, 0, 1, 0, 0, 1. Okay. Now here I am taking the example of z axis being the axis of the matrix, but it could have been any axis. And this is I mean, in one way or the other, so Q would essentially look like this identity matrix plus a skew symmetric matrix. Okay. So you can imagine, if you take out the identity matrix, it's essentially 0 minus theta 0, theta 0, 0, and then 0, 0, 0. Okay. So then,
hello,
so then in that case, the small strain measure, which is 1/2,
হ্যাঁ 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 ওই উল্টো দিকে যে গলিটা, ওই গলিটা দিয়ে চলে আসুন, সোজা খানিকটা এসে একটা,
then you have, if you take Q minus I,
হ্যাঁ হ্যাঁ উল্টো দিকে কালীতারা বসে,
so that would be your skew symmetric matrix. Then your small strain measure is
একদিকে কর্পোরেশন
so
হয়েছে, তার উল্টো দিকের যে গলিটা সেইখানে একটা মানে
if F equals Q, then grad of U must be Q minus I, which would be W, and then your small strain measure is half of W plus W transpose. Now you know this property of skew symmetric tensors, that if you add the transpose, this essentially goes to 0. Okay, so when the amount of rotation is really small, the small strain measure is a valid strain measure. Okay. So, is it clear up to this part?
Yes, sir. This was actually covered.
Yeah, I know this was actually covered. I'm actually saying that uh, that you are if you're comfortable in this derivation, then we can proceed. Actually,
Yeah.
সুমিতের কি ব্যাপার? সুমিত বুঝতে পারছো এই অবধি?
হ্যাঁ স্যার, স্যার এই বেসিক্স থেকে মানে ওইটা ইউটিউবেও আপলোড করা ছিল, মানে প্রিভিয়াস, মানে আর মানে প্রিভিয়াস ইয়ারের কন্টিনিউয়াম মেকানিক্স।
Okay. Okay. So the next topic that we did was to show you that there is a stress measure which, when multiplied with the normal, gives you the traction. Okay, and this is the Cauchy stress. Now, at this point, we need to mention how do we get this traction and what is this traction. So imagine this is the problem. This is a standard problem in solid mechanics. So you have something like a gamma u, where you are constraining the object, and there is gamma t. Of course, the rest of the geometry, rest of the boundary is gamma t, where you could be applying any set of tractions, concentrated moment, concentrated forces, and of course distributed load. But then this concentrated force and moments are also applied at the boundary by means of distributed load. Okay, there is no such thing as a point load. The load must apply to a given amount of area, and if you cannot apply a load without a finite area, and the fact that you cannot also apply a couple moment without a couple of forces, so that means always you need to apply traction. Okay, and now let's say you are somewhere inside the geometry, and let's draw an imaginary plane to somewhere inside. Okay, and the thing is that in a standard problem in solid mechanics, there is displacement, there is force. In gamma u, you have known u. In gamma t, you probably have known force. And this AF everywhere on the body, everywhere, relates to stress. And this everywhere relates to strain. Okay. And the stress and strain relate to each other by means of something called constitutive relation. So I like to think of a standard problem in solid mechanics. Different islands are there, and those islands are connected by a set of bridges. So constitutive relation is one of the bridges. And then there is this bridge which is known as kinematics. Now, what is kinematics? That's what we did for last half an hour, to establish relationship between displacement and strain. And this relation actually comes up through this equation, Cauchy's equation. And this one is Cauchy's stress. Okay. So let's say this is a normal to this plane. Okay. Now, if you take a tiny area in this region on this plane, the plane to which the normal is n hat, unit normal, of course. So on that plane, on that differential area, let's say this differential force is acting. Okay. Imagine you are considering. So this is not an actual plane. This is an imaginary plane. Let's say you are considering the material on this side. So this differential force is acting on this uh, differential area right here. Okay. Now that differential force per unit, the differential area uh, is the traction. That is how traction is defined. Force per unit area. It's like pressure, but uh, now it could also have tangential components. So all I'm trying to say here is that P, the pressure, is actually T dot N with a negative sign. So if T is actually aligned with N in the direction of N, okay, then you have the negative of pressure, because pressure is supposed to be compressive, right? So, but if T dot N is a positive negative quantity, that means you have a positive pressure. Okay, so this is how everywhere within the geometry, that is inside the geometry or the domain or the capital omega, and everywhere in the boundary, that is the capital gamma, you can establish a relationship between the stress components and the traction. So in the end, this boundary condition becomes a set of boundary conditions on the stress components. Okay. Okay. So basically, it turns out this. If I multiply this to let's say E1, okay, I'll get sigma x6, sigma. Okay, so yeah, this is how sigma looks like, not sigma x6. Individual components are sigma ij. So it's like sigma 1 1, sigma 1 2, 1 3, 2 1, 3 1, 2 2, 2 3, 3 2, 3 3, etc. Now if I multiply with E1, and by E1 I mean this vector right here, 1 0 0, and once you have done this operation multiple times, you know that once you multiply with the first basis vector, you are going to get the first column, okay, which is sigma 1 1, sigma 2 1, sigma 3 1, okay, which basically means if I take a parallelepiped of dimensions dx, dy, and dz, so on this plane, which is normal to x-axis, on this plane, so that's what it is saying. This is a normal to this plane. E1 is normal to this plane, right? So this plane is normal to E1. So on this plane, these are the components I'm about to have. Sigma 1 1 along the normal or along x-axis, then sigma 2 1 along y direction, and sigma 3 1 along the z direction. So what do you know now? That the first index is an indication of the direction of the force, and the second index, okay, or the so-called column number, is the indication of the plane. Okay, so sigma 3 1 is acting on a plane which is normal to E1 and acting in the direction of z-axis. Okay, so the first index is for the direction of the force. The second index is the direction of the, or the normal to the plane. Okay, and that way I would ask you to try on your own and you find out the stress components, or that rather the traction. So this right here, sigma 1 1, sigma 2 1, sigma 3 1, is the traction on a plane normal to E1. Okay, so I would ask you to figure out what are the traction on the two other planes. Of course, if you go for the opposite side, you get the negative of t1. Okay, so if you simply change the sign of n with minus n, then it becomes minus t. That's the idea. But what about e2 and e3? I need you to figure that out on your own. The bottom line is the first component or the first index is for the direction of the force, and the second index is for the normal to the plane. Okay, so up to this, I think we believe we covered. And this not only applies to the boundary of the object. You see, the boundary is a term that we need to reconsider. What do we mean by that? Like the way we have drawn free body diagrams, okay, in our undergrads, when we studied rigid body motion and so on. Sorry, when you did engineering mechanics and studied equilibrium of rigid bodies, you take an entire rigid body. Okay, for example, consider this. There is some force applied to it, pinned over here, and then there is another component that is there. Okay, and then we would argue that this member B is a two force member, and the member A, you would have forces coming from the spin, which could be in any two direction, and then over here you have a force coming from the two force member, which is of course the line joining the two pins in the two force member. Okay, let's call that P, and then there is this F. Okay, so this is how we would draw the free body diagram of a single rigid body. But then when we studied beams and drew free bending moment and shear force diagram, we would take a portion of the beam, okay, and draw free body diagram for that. For example, if I were to figure out how much is the bending moment, just 1 second. Okay. So we know that we this plane right here. I mean, we can think of this with this imaginary plane, which separates the geometry into two parts. One of the parts could be thought of as an object on its own. Okay, and since this rule is applied to any boundary, that also applies to everywhere within the geometry. Okay, so we can also do that for internal traction, and that way every point within the geometry, inside of the geometry, is connected to one another using this um, using this equation. So this not only represents the relationship between stress interaction at the boundary, but everywhere within the geometry. Okay, so up to this we did, and mm, and probably we also did this, or maybe not. So imagine, I guess we did this one. So dx dy, I'm taking a differential element, and over here you have sigma x6, sigma x6, sigma yy, sigma yy. I mean, if you want, you can also consider it to be del sigma x6. What is changing? Y is changing. Del y dy. Sorry, I made a mistake. Oh, this one is okay. Sigma x6 plus del sigma x6 del x dx, sigma yy del sigma yy del y dy. Okay, and then there is, so this is a plane which is normal to x-axis, and the force is along y direction. So this is tau yx, and this one would be tau xy, and of course on an opposite plane the traction is simply the negative quantity. Okay, now we are going to show that tau xy equals tau yx. And how do we do that? Actually, you can call this one as tau xy and this one as tau yx, and you can simply call this one as tau yx plus del tau yx del x dx plus del tau xy del y dy. Okay, but actually none of that matters. Okay, we are not going to subtract anything from here. So basically, if you take moment about any point, okay, so essentially this tau yx over here and this tau yx over here forms a couple, and the net moment about z-axis is going to be uh, tau yx times, and if you want to add this term also, this is of course it's an infinitesimally small term because it involves a dx term, but this tau yx times dx. Okay, now first of all this tau yx must be multiplied with dy times 1, assuming there is unit thickness to this differential element, which gives you the differential force. Okay, and then multiply with gx to get the moment due to this tau yx traction. Okay, and that's a counterclockwise moment. Then subtract tau xy times dx times 1, the differential force, times dy. And if we assume there is no distributed moment, okay, like let's call it bn, a distributed moment, that means in a differential element there is some moment. Okay, uh, if there is no such thing like a distributed moment, okay, which is true in most cases. I mean, the simplest example that I can think of distributed moment is when you induce a magnetic field, let's say in a motor or a generator, on the armature or the stator parts. Okay, And when you induce that magnetic field, there could be distributed moment. It's basically because of that moment the armature rotates. Okay. Um, but apart from such examples, the distributed moment could be nullified, and in that situation, okay, you can say this tau yx equals tau xy. Okay, which sorry, not tau xy. Yeah, I should be using sigma. I'm using tensorial notation, so I should be using all sigma. Okay, so all of these are sigmas, by the way. So sigma, 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 sigma. So sigma xy is sigma yx. That's the idea. Now, now at this point, we know that the stress tensor, which automatically pops up from the solid mechanics formulation, is also a symmetric tensor, just like the strain tensor. We didn't choose it to be, but it's due to the angular momentum balance. I mean, I could do the same operation for any plane. Here I have taken xy plane, but I could be taking xz or yz plane. There also such relation should be true. So now we know that all the terms in the stress tensor, I mean, all the off-diagonal terms uh, obey the symmetry condition. So the stress tensor is a symmetric tensor. And the similar way I can represent the stress as in a void notation, something like, okay, so the stress tensor is a symmetric tensor. And I can also represent that using a void notation, because only 6 components are independent. The 3 are dependent components because of the symmetry. Okay, so we had two set of equilibrium equations. One was angular momentum balance, and actually I should not be calling them equilibrium equations. They are balance equations. Okay, like conservation of mass, conservation of linear momentum, conservation of angular momentum. These are balance equations. So angular momentum balance results into this representation, and then there is linear momentum balance. Okay, see. What is the essence of the symmetry of the stress tensor is, so the thing is the angular momentum balance would give us that once we applied some sort of torque, that is sorry, the net moment applied should be I alpha and so on, so many things. Actually, I would be a matrix, okay, or maybe even a more complicated expression that is there. But the thing is, when it comes to stress components, this essentially is moment is a vector, and there are 3 components. So this essentially represents three equations. There are those 3 equations. Okay, imagining this that there is no acceleration. Okay, those 3 equations actually do not take place. I mean, do not add to the number of equations to our problem. What it does is it just reduces the number of independent components in the stress matrix by 3. So if we didn't know that the stress tensor was symmetric, there were nine unknown components. Now we know that it is symmetric, so we have 3 less unknown components. So there are 6 independent components. Okay, so that's how the angular momentum balance plays a role in the equilibrium equations. Okay, and let's now talk about the linear momentum balance. And for that, again, I'm going to take a 2D element because it is easily verified in the 2D. So again, this one is a dy element, this one is a dx element. This, of course, is the x direction. This, of course, is the y direction. So here you have sigma x6. This one is sigma x6 plus del sigma x6 del x dx. This is sigma yy, and this one is sigma yy plus del sigma yy del y dy. This is tau yx, this is tau xy. Acha, sorry, this is tau xy, and this is sorry, sigma xy. This is sigma yx, and this is sigma yx plus del sigma yx del x dx, sigma xy plus del sigma xy del y dy. 1 minute. Okay, so the equilibrium equation, let's say if I write the equilibrium equation in x direction, so the net force in x direction is first of all, this is sigma xx plus del sigma xx del x dx times dy times 1, which basically makes the differential area. But then there is sigma xx in the opposite direction as well. So here you have this. Acha, no, sigma xx times dy. And then you have sigma xy, this one, plus del sigma xy del y dy, this thing acting on differential area dx times 1 minus this is yx and this is xy, sigma xy times dx acting in the opposite direction. This plus if there were any body force, uh, what is body force? Like force due to gravity, okay, and it is typically represented mm, with acceleration due to gravity. So that is the force per unit mass, okay. That is W by m, or W equals mg. So what is body force? Now there are two types of forces. One is traction force, which happens through contact, okay. So you can load a beam by putting weight on top of it, okay. So that would be the uh, traction force. But if you load the beam, let's say the beam is made of mm, steel, and if you want to load that by applying a magnetic field on that, okay, so this type of field forces, electric field, magnetic field, gravitational field, okay, all of these forces which act from a distance, and a force which doesn't only apply to the boundary but everywhere inside, okay. So those set of forces are called body forces. Traction forces are those which are applied at the boundary. Okay, you can only apply them at one of the boundaries, at one portion of the boundary, one part of the boundary. But the body forces, they act distributed over the volume. Okay, and they act in a non-contact mode. Okay, they act through a field. So all of those body forces combined together could be generalized into this acceleration b, and that is the force per unit mass. To get the force for the, you know for this differential element dx dy, we have rho, the density, times dx times dy times 1 for the third dimension. And there is a net force acting on this geometry. And on the right hand side, then you have rho dx dy times ux double dot. So it's basically, this thing is Newton's second law of motion, but not for a particle, because Newton proposed the law for particle. But this thing is not for particle. This is for a differential element. So you have this, body of finite dimension. You took a differential element of length dx and dy, and basically for that you get this equation, equation for linear momentum balance. Okay, so rate of change of linear momentum is the sum of the net forces, I mean net sum of the forces. uh, so if you simplify this, then you have this, see, this term and this term will cancel out, this term and this term will cancel out. So you have and eventually you will be able to divide everything with dx and dy everywhere. So you have del sigma xx del x plus del sigma xy del y plus rho b equals rho ux double dot. Acha, bx by the way. Okay. And actually, if you add the third dimension, and you also consider the third set of shear stress components like xz and yz, then you have this equation. So this is 2D. In 3D, you have del sigma xx del x plus del sigma xy del y plus del sigma xz del z plus rho bx equals rho u ux double dot. So there is only one extra term, but this time, this type of equation you will get three. So in 2D there would be two equations of equilibrium. In 3D, rather two equations of motion you can call. In 3D there would be three such equations. Okay, so so uh, so for I between 1, 2, and 3, you can write this equation: summation over j del sigma ij del xj, basically representing these three terms. And since I didn't write the equations for y and z, that's what I am writing for I going from 1 to 3. So let's say when I equals 1, you have the equation in x direction. When I equals 2, you have the equation in y direction. And I equals 3, you have the equation in z direction.
Direction.
Plus rho bi equals rho ui
UI
double
double
dot.
dot.
Okay, this is the, the generalized 3D linear momentum balance equations. Okay, of course, with equilibrium, u double dot equals 0. Okay, so you are left with del sigma ij del xj plus rho bi equals 0. Okay, for all I, so this is for all symbol, for all I in 1 to 3.
1, 2, 3.
Okay, now and this is where we would end today's discussion, is that this entire representation could be, written in 3D. I mean, written in vector form. So this is a scalar. Each component I'm writing. This is for three different i's. You'll have to write this equation thrice. So basically, if you club these three equations, basically it's a vector equation, and that vector equation is divergence of stress. You remember divergence? If you take divergence of u, okay, which is a vector, that would be summation over del uy del xi going from 1 to 3. It's a scalar, okay. So that's why it comes with a dot product symbol, as if you are taking a dot product with the partial derivatives, okay. Essentially it represents, um, so for a vector you get a scalar. For a tensor or a second order tensor or a matrix, you would get a vector. So it's a vector actually, okay. And basically the ith term, because it's a vector, so the ith component of this one is del sigma ij del xj, summation over j, of course. Okay. So basically, the sum of these three terms forms one component of that vector, plus rho times b, this time like a vector, okay, not component, equals zero vector, okay. So this is our equilibrium equation in 3D. And for this one, we would like to write our, the variational form. I mean, if you compare this to the 1D bar equilibrium equation, it is like d sigma x dx equals 0, or e, what did we do? We also multiplied with area. So ea u double prime equals 0 or something, okay. So imagine the 3D version of it, which involves a lot of partial derivatives. Uh, One more thing about constitutive relation. Okay, we have already made ourselves familiar with constitutive relation. For example, in 1D, this is what a constitutive relation looks like. Sorry. So the stress relates to strain using the Young's modulus. Okay, so that's a constitutive relation. 1D, of course, but in the next class, we would learn about 3D constitutive relation. Okay.
Okay.
Okay. Okay, sir.
Okay.